Hello my dear students, welcome back to Learn Physics. In today's topic, we are going to discuss about the dual nature of matter and radiation. In last class, we learned about the photoelectric effect, that is laws of photoelectric effect and Einstein's photoelectric equations. Right? So today we are going to do some numericals related to that. Okay, so first question is, the following table gives the value of work function for a photosensitive material. If each of these metals is exposed to radiations of wavelength 300 nanometer, which of them will not emit photoelectrons and why? This is the question. So here it is given like sodium has a work function of 1.92 in electron volt and potassium 2.15 electron volt and molybdenum that is 4.17 electron volt. So these are the work functions of certain photosensitive metals. Each of these metals is exposed to radiation of wavelength 300 nanometer. So these are exposed to a wavelength of 300 nanometer. And which of them will not emit photoelectrons and why? For that H value is given. You know that 6.6 into 10 to the power minus 34 joule second. Okay, how can we find out the value of this? See, which of them will not be giving, will not give this. So we are giving a wavelength of 300 nanometer. Work function is given. What is meant by work function? Work function is the minimum energy required for the electron to give out the electrons. Right? So this one, what is the minimum, what is the energy for this wavelength? That one we can find out. E is equal to h nu, that is hc by lambda. H value we know 6.6 into 10 to the power minus 34, 3 into 10 to the power 8 divided by lambda is 300 into 10 to the power minus 9. Okay, so here we will be getting it as 100. 3 and 3 will get cancelled. So 6.6 into 10 to the power minus 26. Here it is 10 to the power minus 7. When it is coming to numerator, it will be 10 to the power minus 19. So here this is in joule. We can convert this in electron volt because here in all the values are given in electron volt, right? So 6.6 divided by 1.6 into 10 to the power minus 19. So here what will be the value? 3 point something. 3.8 something, 3 point something will be getting as electron volt. Okay, so here this much of energy is incidenting. So minimum energy required, minimum this much of energy is required. So 3.8 electron volt, 1.92 electron volt. We are giving 3.8 electron volt to the sodium. So for sodium it requires only 1.98. So we are giving more amount of energy. So it will take out the electron. So what it will be doing for with the rest of the energy? It will be as per electrons, this Einstein's photoelectric equation. We know that it will be coming out. It will be used for the movement of the electron. And 2.15. Now you tell whether it will take place. Yes, photoelectric emission will take place here since work function is less. The work function of potassium is less than the given energy. What will happen to 4.17 electron volt? Here alone this reaction won't, this photoelectric emission won't happen. Clear? Next question, by how much would the stopping potential for a given photosensitive surface go up if the frequency of incident radiations were to be increased from 4 into 10 to the power 15 Hertz to 8 into 10 to the power 15 Hertz? If we are increasing the frequency from 4 into 10 to the power 15 Hertz to 8 into 10 to the power 15 hertz. How much will be stopping potential? How much increase will happen for this stopping potential? So what is the relation connecting this frequency and this stopping potential? We know that as per Einstein's photoelectric equation, say energy will be equal to half mv maximum square minus or kinetic energy plus work function. Okay, well, what is work function h nu 0? So h nu equals half mv maximum square plus h nu 0. Nu is the frequency. So here it is asking about the potential, stopping potential. Here in this stopping potential value itself is not there. How we will find out? We know half mv maximum square is equal to EV0, right? So h nu plus h nu 0. So V0 formula is h by E into nu minus nu 0. Okay, this is the stopping potential value. Now we need to find out the difference. What is the increase which is happening? We are giving a potential of, we are increasing the frequency from 4 to 8. 4 into 10 to the power 15 to 8 into 10 to the power 15. So this is V01 for h nu 1. Then what will be for V02? V02 will be equal to h by E is constant, nu 2 minus nu 0. Nu 0 is remaining the same because this threshold frequency that is remaining same for the same metal, right? So here we are increasing the frequency alone. Difference in potential. I'll write down here. V02 minus V01 will be equal to h by E into nu 1 minus nu 2. H we know 6.6 into 10 to the power minus 34 divided by 1.6 into 10 to the power minus 19 into nu 1 minus nu 2 or nu 2 minus nu 1. Nu 2 minus nu 1 is 4 into 10 to the power 15. Yeah, we will get it as, here it is 4.4. So here 660 divided by 4 means 660 divided by 4 into 10 to the power, here it is minus 19 will get cancelled. You will get it as, so here somewhere I missed out my 16.5 only it is getting, 16.5. I think somewhere I went wrong with my calculation. 4 into 10 to the power 6.6. Here it is 6.6, right? So that is why we are getting it as 16.5. This will be the potential, 16.5 volt. Clear? So this is how we will be finding out the difference in what is that potential, stopping potential. The graph shows the variation of photoelectric current versus applied voltage for two different photosensitive materials for two different intensities of incident radiations. Identify the pairs of curves that correspond to different materials but same intensity of incident radiation. Materials are different. So here the graph is given like between I and V. This is potential and this is number of photoelectrons or current we will be representing. So here one graph is given like this and another one is given in another point. Okay, and another one is given like this and from here itself another one is coming here. Okay, this is first one, this is the third one, this is the second one and this is the fourth one. This is the graph. Here it is no difference at all, it's constant. Now I'll read out the question once more. I versus V graph. Identify for two photosensitive materials for two different intensities of incident radiation. Identify the pairs of curves that corresponds to different materials but same intensity of incident radiation. Materials are different but same intensity. Same intensity means which and all having same number of same saturation current. or for a particular value it will be having the same intensity. Same intensity of radiation means it will be, yes, here which and all will be getting maximum, same. So for a particular voltage, here saturation current is same for 1 and 3. Here for 2 and 4 it is same. So 1 and 3 will be having same intensity. 2 and 4 will be having same intensity. Okay, clear? So intensity means it depends on the number of free electrons. So whatever be the frequency, whatever be the material, we will be getting the, for the same intensity, we will be getting the same number of electrons. So current is same, then we will be getting the same intensity. Clear? So the next question is, when a given photosensitive material is irradiated with light of frequency nu, the maximum speed of the emitted photoelectrons equals Vmax. Then the square of Vmax is observed to vary with nu as per the graph shown below. Obtain the expression for Planck's constant, work function of the given photosensitive material in terms of the parameter I and N, the I, N and the mass of the electron. So I'll draw the graph here. So this is the graph given. This is Vmax square and nu. This is L. I read it as I guess. So it is L and this is N. So we need to write down obtain the expression for Planck's constant, work function of the given photosensitive material in terms of L, N and M. How we can write down? Here we know that Einstein's, this equation, this kind of graph is related with Einstein's photoelectric equation. So we know that h nu is equal to half m Vmax square plus h nu 0. Okay, so if we are writing down the equation in terms of Vmax square, because here the question is given like Vmax square and nu. So we should get that relation first. So half h nu minus h nu 0 into Vmax, right? 2h nu by m. So while we are finding out an equation, h nu minus h nu 0, 2 will be cross multiplied and m will be divided. So this is the relation. I can write it as 2h nu by m minus 2h nu 0 by m. Right? So here h is constant, nu 0 is constant, m is constant. So this is the equation. Since it's a straight line from the graph itself, we can identify. So here y is equal to mx plus c. So y axis is Vmax square. M is, what is m? 2h by m. This is the slope of the graph. So here slope of the graph will be equal to 2h by m. Therefore h is equal to m into m by 2 into slope. This is how we will be finding out the what is that, h value. Now see, what is the y-intercept? 2h nu by m, that is L. Therefore, we can write down the work function. Next, we need to find out the work function, right? Work function equals, work function only we need to find out. For that, constant value is 2h nu 0 by m. That is the y-intercept, but here it is given as L. Therefore, it is equal to L. H nu 0 equals ml divided by 2. This will be the h nu 0 is the value for work function. Therefore, h nu 0 equals 2 into ml divided by 2. And here you can find out the slope of the graph. Slope, how much it will be? L by n. So ml by 2n. This will be the value of Planck's constant. So from the equation, from the graph, we can find out all these values. Clear? Next question is, Figure shows a plot of three curves A, B, C showing the variation of photocurrent versus collector plate potential for three different intensities I1, I2, I3 having frequencies nu1, nu2, nu3 respectively incident on a photosensitive surface. Point out the two curves for which the incident radiations have same frequencies but different intensities. So first I will draw the graph. Here photocurrent and this is the potential, and here it is given like I1 and this is I2 this is I2 and next is I3. This is I3. Okay, curve A, B, C. Now point out the two curves for which the incident radiation have same frequency, different intensities. Intensity is different, frequency is same. If frequency is same, we know that stopping potential will be same for same frequencies. Right, frequency and stopping potential are directly proportional, and as the frequency increasing, according to that the stopping potential also will be increasing. For the same frequency of light, it will be having the same stopping potential. So here I2 is greater than I3, but this for A and B having same frequency. Since the stopping potential is same, we can identify that as they are having the same frequency. Clear? So these kind of graph questions can expect more in the case in this dual nature of matter and radiation, that too in particularly in photoelectric emission. Okay, clear children? So I hope today's class is useful for you, and if you like the channel, please don't forget to subscribe, like and share. Thank you for watching. Bye.